Hello everyone, I'm Viktor Zaitsev from Samsung R&D Institute Ukraine. Today I'd like to present you PIX-TAB, our approach to efficient pixel-precise table structure recognition. Tables are everywhere in documents, and table structure recognition sounds deceptively simple, but it's one of the harder problems in document AI. Real-world tables vary enormously in layout. They have merged cells, complex nested headers, missing borders, and irregular spans. Long and complex tables are particularly difficult to decode correctly. Most existing solutions fragment the task. They use one model for detection, another for structure parsing, and yet another for text recognition. This creates error accumulation pipelines. Moreover, nearly all state-of-the-art models require server-class GPUs and are trained on datasets only cover simple clean table layouts. Our motivation with PIX-TAB is to close this gap. A single small fast model that runs on device, handles complex tables, and stays language agnostic. Our approach, PIX-TAB, consists of four tightly integrated components. First, an encoder-decoder model that predicts both OTSL structural tokens and our novel position-aware pixel-precise tokens. Second, a region-based image segmentation module, or RBIS, which handles tables with complete visible borders through flat fill. Third, an external OCR model for text content, which keeps the system language agnostic. Swapping the OCR is all that is needed to support a new language. Finally, an aggregation module that applies a hybrid selection strategy to pick the best output between the encoder-decoder and RBIS paths. A core innovation in PIX-TAB is our compact table representation. Rather than predicting bounding boxes with a separate decoder head at inference time, we encode spatial information directly into the token sequence itself. We introduce row start tokens, which encode the vertical pixel coordinate of each horizontal table line, and column boundary tokens, which encode the horizontal pixel coordinate of each vertical table line. These are mixed with just 4 structural OTSL tokens. Because the coordinates are encoded into the tokens, the complete set of cell bounding boxes can be reconstructed deterministically from the sequence alone. No separate bounding box decoder is needed during inference, and as the slide shows, this token sequence is about half the length of the equivalent HTML representation, which makes training and inference faster. By design, transformer decoders generate tokens one by one, which makes them slow. Speculative decoding is a known technique to accelerate this, but it typically requires a second, smaller draft model. We avoid that entirely, because PAP OTSL sequences are highly regular across rows. We can build token hypotheses analytically using simple rules, no extra neural network. After decoding the first row, our algorithm predicts future tokens by detecting repeating row patterns and estimating the next row's vertical position from the pixel spacing seen so far. A single forward pass then verifies the speculative block. Accepted tokens are kept and the first mismatch ends the block. This reduces the number of decoder steps dramatically for regular tables. The encoder-decoder model handles most tables well, but struggles with large, dense tables that have all borders visible, a very common format in enterprise and marketing documents. For this, we designed a complementary module, region-based image segmentation. The algorithm works in 3 phases. First, region detection, starting from each unvisited pixel. A flat fill expands connected regions of similar intensity with a tolerance of intensity levels. Second, region analysis. For each expanded region, we compute its bounding box and density ratio, the proportion of filled pixels to bounding box area. Third, quality filtering. We retain only regions whose density and minimum dimension exceed empirically set thresholds. The result is a set of clean cell bounding boxes extracted purely from image geometry without any neural network. The time complexity is linear since each pixel is visited exactly once. To evaluate our approach, we use the standard TEDS and TEDS struct metrics, which are based on tree edit distance. However, we identified a key weakness. A high average TED score can mask the fact that many individual tables still contain at least one structural error. A model that gets 99% of cells right but consistently mishandles one cell per table would report a near-perfect average, yet fail on every single table. To address this, we introduced two new metrics: TEDS struct 100 and TEDS 100. These report the proportion of tables where the entire structure and content is recognized. These metrics give a far more honest picture of practical reliability. To assess the impact of training data diversity, we compared three training configurations using the original dataset alone, augmenting it with the existing SynthTabNet data, and augmenting it with our own proposed synthetic data generator. Across all settings, our approach delivered consistent improvements. In terms of speed, comparing PIX-TAB to recent state-of-the-art methods on FinTabNet, our model achieves near 8 FPS, outperforming many competitors in throughput, while maintaining competitive accuracy. Finally, on mobile hardware, our optimized model processes tables in just 6.6 seconds on average, compared to 19.9 seconds for the full model, representing a speed up of over 3 times with only a marginal accuracy drop. Now, let's look at the ablation study, where we systematically evaluated the contribution of each key component of PIX-TAB to the final performance. The results show that adding speculative decoding preserves recognition quality while significantly reducing decoding steps, which directly translates into lower latency and better suitability for on-device deployment. Enabling region-based image segmentation brings additional gains on large tables with complete borders, where the pure encoder-decoder model struggles, demonstrating that the hybrid design effectively handles challenging real-world cases. Let me now walk you through the main takeaways of our work. First, we introduce a compact table representation built on position-aware pixel-precise tokens combined with analytic speculative decoding to accelerate sequence generation without compromising recognition accuracy. Second, we propose two new metrics designed to address the well-known shortcomings of existing table structure recognition evaluation measures. Third, we present a region-based image segmentation approach which enables reliable cell detection specifically for tables with well-defined geometric boundaries. And finally, we describe a comprehensive synthetic data generation pipeline that overcomes the limitations of currently available datasets for table structure recognition. Thank you very much for your attention. Our contact emails are on the slide, and we look forward to your feedback.